Okay, so we're on paper 5 paper from the A2 level, A level from Cambridge International Exams. Paper 5 is all about planning, analysis, and evaluation, looking at not particular chemical knowledge that you know, but your science skills for constructing and analyzing experiments. This is from June 2014. And the paper is for 1 hour and 15 minutes, so we should get through that comfortably in the masterclass today. And as we go through this paper, what I'd like to do is emphasize a couple of things. One is, again, all the kind of comments that the examiners are making, so typical problems that students have. And the other thing that I'm going to throw in today as well is an emphasis on vocabulary, the language that you use, because when you come to an exam and you're under time pressure, if you can use the right word, you've got it done in one word, rather than writing a whole sentence to say what you mean. Okay, so if we can look at what the examiner said and check our vocabulary, then I think we're making some real development to our exam skills, as well as checking the science in the paper as well. All right, so this first question is about magnesium nitrate 5 being heated, the thermal decomposition of group 2 nitrates. And if you've been following along with the master classes, this thermal decomposition of group 2 nitrates seems to be occurring in every paper that we've looked at. So it seems to be a very, very common thing that they're testing. And first up, you've got to write the equation for the thermal decomposition of magnesium nitrate. And so, I mean, we could look that up, but because it's being asked so regularly, we should just make sure we've got that in. So this is magnesium nitrate 5. There it is. And we're heating that. We're going to white magnesium oxide. We've got brown gas, nitrogen dioxide, and we've got oxygen gas. And when you have to do all the balancing up, the stoichiometry of the equation, you get all of that. And then it continues down, and it's just checking that you can do a few simple calculations here. You've got to know that you've got a stoichiometry of 2 to 2 to 4 to 1, and later on it asks you to work with 1 mole of magnesium nitrate, so your stoichiometry is that, and you end up with 0.05 moles of oxygen. And you have to know, don't you, that 1 mole of oxygen, or any gas, would occupy 24 decimeters cubed under room conditions. So later on, when you're starting with 1 mole of magnesium nitrate, you're going to end up with 12 decimeters cubed of oxygen. So the point the examiner made was that the students were doing these kind of calculations and they were coming up with the right numbers, but they were forgetting their units. So to get the full marks on this question, you've got to make sure that you had not just the numbers, but also the units. Okay, because they also asked you, didn't they, the mass of magnesium oxide, and that came to 40.3 grams. Okay, again, a value and a unit. And so when you're maybe expressing yourself later on, you need to be able to distinguish between a quantity, its symbol, which is getting into some of the vocabulary here, the value, and the unit. Okay, so this is not a weight, it's a mass. So the quantity is a mass. The symbol for mass is a little m. The value was 40.3, and the unit was a gram. And that quantity was a mass. Yes? Same over here. The quantity was volume. The symbol is V. The value is 12, and the unit is decimeters cubed. Yeah? So you just got to make sure that you can express yourself clearly. And the one that students don't know, of course, is when the unit is mole. You could look up, I don't know, the value, you've got some value for moles. The symbol is a small n, isn't it? And the quantity is amount. That's technically the right word for saying the number of moles. So you could be writing in your exam paper the number of moles, that's 4 words, but if you just said the amount, bang, you're done. And it sounds like you're not being clear, because we use the amount word in everyday language, but its specific meaning in chemistry is the number of moles. So if you want to say the number of moles, you just say amount. That's the quantity. Good. Okay, so just a little bit of vocabulary there, and the examiner was concerned that students weren't including their units properly. Now, here you had to draw a diagram, and the examiner gave a really, really long criticism of all the weird diagrams that students created. So we'll just look at what the diagram should look like, and then kind of pick up some of the things that the examiner was concerned about. So if I was drawing this, I would have here a tube, and you don't have to draw Bunsen burners or anything like that. An arrow with heat underneath is sufficient to show that you're heating this tube. All right, and in there is the magnesium nitrate that we're going to heat. Now, we said in the last masterclass the examiner was complaining about students using pencils, and that's true when it's a structured answer paper, but when it comes to drawing a diagram, of course, pencil and ruler is absolutely fine. You know, that's almost expected, actually. And as we heat this magnesium nitrate, it's going to decompose. We want to capture the gases that are being given off. And so you have to excuse me because I don't have a ruler and all of that, but there's a bung at the front of that tube, and the bungs you just shade in. Okay. All right. And one of the complaints the examiner had was that this experiment the products were gases, and students had drawn the apparatus which wasn't airtight, and so the gases were kind of leaking out everywhere because you hadn't drawn having a bung in there to okay, so and you've got just the arrow there for heat, and you should label up. Oh, you can do chemical formula. The magnesium nitrate is in there, and I'm struggling with my computer pen here. These should be drawn horizontally. Sometimes people kind of put labels at all sorts of angles, but you're writing as if there were lines on the paper, even though there aren't lines there. And then to go from your label to the diagram, that should be a straight line drawn with a ruler. Okay, don't do kind of wiggly lines. So a label on a straight line, as if it was a writing paper, and a straight line drawn with a ruler for your magnesium nitrate. And this is, you could just say this is it's some kind of test tube, isn't it? You can just say that's a heating tube. All right. And then you've got this glass tubing here, and we've got the two gases coming along there. And the glass tubing is going to go into a nice flask down here. Okay. So this is my flask. And I've got another tube coming out the top there. And again, the examiner was complaining that students hadn't sealed the apparatus. We don't want any gases to leak out. And so there's another bung, which is going across the top of this flask here. And you can see my glass tubes properly go through the bung like that. And I can just shade the bung in there. Now, the reason I've drawn one tube long and the other tube short is that in here, it told you in the question that, well, we worked out that's coming along this glass tube here when we heat it. Well, what's coming along there? It's a mixture, isn't it, of the nitrogen dioxide gas, comma, and the oxygen gas mixture. That's coming along that first tube as we heat the magnesium nitrate. So that mixture of gases is going to come along here, down here, and then it's going to start to bubble through this here. And the question told you that nitrogen dioxide is completely absorbed when it bubbles through an alkali. Yes? So this is an alkaline solution here. And so as the gas bubbles through, you no longer are going to have a mixture of gases because the nitrogen dioxide has been completely absorbed by the alkali. And so the only thing that's coming through this glass tube here is oxygen. So we've properly separated out those two gases, haven't we? Now, we've absorbed the nitrogen dioxide. We've just got the oxygen gas traveling through this output tube here. It's just a gas. The way to measure a gas, the easiest way to do that is with a gas syringe. There's other things that you could use, but and so there's a plunger there to the gas syringe, isn't there? And the gas syringe will have a scale on it so we can measure the volume of gas that's being collected. So that's gas syringe. There's a label and a straight line drawn up to that. And over here, this was the flask with an alkaline solution in it. Okay, so that's the basic apparatus that you'd use for doing this. Let's just go through some of the things that the examiner picked out. Not drawing in pencil, not drawing in straight lines, were some of the things. Not putting these bungs in, so gas was kind of escaping everywhere. And then, strangely enough, even though you had a mixture of gases here, some students somehow had like a Y junction in the tubes and assumed that somehow the gas magically separated into oxygen and magically separated into nitrogen dioxide, and they had two gas syringes. So they were coming up with this strange apparatus which wouldn't work. But you know from the question that the alkaline solution will absorb the acidic gas, nitrogen dioxide, and that means the oxygen gas is freed up to travel onwards to the gas syringe. The other thing that the examiner picked up as well was that students didn't have a feel, didn't have a sense for what appropriate volumes were. So I'm going to call my gas syringe a 250 centimeters cubed gas syringe. So 250 centimeters cubed is, well, I don't know, that's a quarter of a liter, isn't it? Yes? So you can imagine that's a reasonable volume of gas to collect in an experiment. Because some students weren't really thinking very carefully, the examiner said, well, some students had a gas syringe of volume 50 decimeters cubed. So that's 50 liters, which is, can you imagine that? That's enormous piece of apparatus, which is completely inappropriate for this kind of experiment. So, you know, you've got to have some feel for the kind of volumes that you typically work with in a laboratory, and then say, well, a gas syringe of about a quarter of a liter or half a liter sounds about the right size for the kind of measurements that we do in the laboratory. Okay, good. And then later on, it starts to say, well, okay, you've got to calculate roughly the masses and the volumes that you think you're going to work with in this experiment. And because you'll have done something different, but because I put a 250 centimeter cube gas syringe in there, I want to make sure that I don't overfill that syringe, because it'll be difficult to measure if it goes beyond 250 centimeters cubed. So when I came to my calculation down here, I assumed that the most gas that I would collect over here would be no more than 200 centimeters cubed. So I'm not going to overfill my gas syringe. So that was my starting point. And once I worked out, well, no more than 200 centimeters cubed of oxygen, then I could work out how many moles of oxygen, the amount of oxygen, and then I could work out the amount of magnesium nitrate that I needed, and then I could work out the mass of magnesium nitrate that I needed. And so when I did all those calculations, I came, you'll have something different, but they'll all be equivalent. So I had, well, I think I'm going to calculate starting from 200 centimeters cubed of oxygen. And when I worked through the calculations, I ended up saying that I needed to measure a mass of 2.46 grams of magnesium nitrate. And that's quite comfortable because that's the kind of order of magnitude of a chemical you can easily weigh out on a top pound balance in a laboratory. It's 2.5 grams. That's something that's absolutely normal mass to be able to work out. And so what I was doing, I was saying from 200 centimeters cubed of oxygen, then I could work out this is my N, the amount of oxygen, and then I could work out the amount of magnesium nitrate. And from the amount of magnesium nitrate, I could work out the mass of magnesium nitrate, which is, you're doing the calculations to help you set up your experiment in the lab. You'll have different values, but they've got to make sense. You can't be like these students having 50-liter flasks around because you'd end up with like, I don't know, 50 grams of magnesium nitrate or something. This is, you know, these values are much, much too big. Those are the values that I chose. You'll have your own ones. And the other thing the examiner pointed out here was that when students are doing these kinds of calculations, they round up their significant figures or decimal places much too early. So you can do your calculation, and I think I ended up with 2.461 grams of magnesium nitrate, and I only rounded at the end. I didn't try and round my calculations earlier because then I get an error being carried through my calculations. So keep your calculations to 4 decimal places as you go through, and then when you get to the end, you've got an answer to 4 decimal places, and at that point, round it. Don't do the rounding too early. And that was one of the criticisms the examiner made. Good. All right. Now, you've got a list here all the measurements that you would do when you're carrying out the experiment. And the principle for all of these is you are, and it's, you know, it's a principle in a lot of laboratory chemistry, you are measuring, well, in this case, we're measuring a mass for a lot of these. You're measuring by difference. I'll explain what that means in a moment. But with respect to the tube where the magnesium nitrate is that you're heating, the first measurement you're going to make is the tube with nothing in it. All right? So empty tube. The next measurement you're going to do is the empty tube plus magnesium nitrate. Well, I can just call it a tube at that point, can't I? Because it's no longer empty. And the third one is going to be the tube with what's left over at the end of the experiment, which is the magnesium oxide. All right, so I've got those masses, and I work out the mass of magnesium nitrate by difference. I subtract 1 from 2. And to work out the mass of magnesium oxide, I subtract 1 from 3. I'm measuring a mass by difference. Yes? Because what you don't want to do is have a tube at the end and kind of scrape out all the magnesium oxide and take it off somewhere and measure the mass, because you're going to lose things along the way. So if you do this technique, it's not a very complicated technique, of measuring the mass by difference, then there's no chance at all that you'll lose any of the chemical through any processing or transfer. So, you know, this is quite good vocabulary. You can quickly say, in all this experiment, I'm doing my measurements by difference. And then the examiner knows that you're doing appropriate ways of measuring the mass by subtraction rather than just trying to measure a mass on its own. So that would give us the mass of magnesium nitrate to start with, and that would give us the mass of magnesium oxide to finish with. For the collection of the oxygen gas in the gas syringe, that's easy. You just set the gas syringe to 0 to begin with, and the plunger of the syringe will move. So that's an easy one to measure. So you can just, the measurements that you're going to make, you're going to be taking a volume measurement in the gas syringe. And you could say that at the start of the experiment, you set the syringe to 0. Well, that's a kind of fairly obvious point. It don't have to be explicit. And then if you look up here, as the nitrogen dioxide bubbled through that alkaline solution, that nitrogen dioxide is first dissolving in the solution and then reacting with it. Okay, so the nitrogen dioxide is staying in the alkaline solution. That's where it went. Now, although we don't think of it like this, of course, a mass, a gas has a mass. You know, the nitrogen dioxide, even though it just looks like a brown gas, it still has a mass that you can measure. And so to measure the mass of the nitrogen dioxide gas, we do that by difference again. We have the mass of the flask with the alkali in it at the start, and we have the mass of the flask and the alkali and the nitrogen dioxide in it at the end. And by subtracting those two, that gives us the mass of the nitrogen dioxide that's dissolved in the alkali. All right? So you've got another difference to do, where you're going to do the flask plus alkaline solution on its own at the start of the experiment, and at the end you're going to have the flask plus the alkaline solution plus all the NO2 that has dissolved in it and reacted with it. And then to work out the mass of the nitrogen dioxide, the NO2, you just subtract 5 from 6. We're measuring a mass by difference. So you can see how this idea of using a difference works its way through. You know, in this experiment, we had to do it twice, didn't we? Once here for the solid and once here for the mass of the gas. Yes? So we're measuring mass by difference. Okay, so we've got to make sure in this experiment that the experiment has gone to completion, that all the magnesium nitrate has fully decomposed. And the classic way to do that is to, and this is where vocabulary is good, heat to constant mass of, well, you're getting to magnesium oxide at the end, aren't you? So you can see there, the examiner or the exam has given us 3 lines, so we could be writing loads of stuff in there, but the technical word or technical phrase is just to say you heat to constant mass. And what that means is you heat it for a while and you think the reaction's over and you measure the mass. You heat it again, nothing seems to happen, and you measure the mass, and the mass has maybe changed a little bit, so you think, oh, the reaction's still going. So you heat it again, take another measurement of mass. This time the mass hasn't changed at all. Heat it again, take one final measurement, and when you've got 2 or 3 consecutive measurements that show no change in mass, you've heated to constant mass, then you know the reaction is over. All right? So that you can either say all that like I did in a long sentence, or you can just say, I would heat to constant mass of magnesium oxide, and the examiner knows exactly what you're talking about. Good. All right, so we were talking about making sure we've got good data. We heated a constant mass, but we've got to take care because we want to measure a volume. Now, a volume, of course, is affected by temperature and pressure. Yes? So if you heat up a gas, then it can expand. The volume can expand. Or if the pressure changes, then the volume of gas will change as well. Now, so, I mean, we don't have to worry too much about pressure. During the course of the experiment, the pressure in the room isn't going to change very much. But we do have to worry about temperature, because we've been heating this magnesium nitrate up with the Bunsen burner. And even if we haven't heated the gas syringe, and that's not a good idea, you shouldn't do that anyway, the gas might still be warm because it came from really hot magnesium nitrate and bubbled through. The oxygen gas we collected might not have been at room temperature. So you've just got to be careful that when you're measuring the volume of mass, sorry, when you're measuring the volume of gas, that the syringe has properly cooled to room temperature. So to make sure the volume of gas measured is accurate, what should you do before taking the measurement? You have to ensure gas syringe is at room temperature. Because they've told you that 1 mole of gas occupies 24 decimeters cubed at room temperature. And if you're not at room temperature, then the mole of gas occupies a different volume, and you're doing all these calculations based on the volume and going from that volume to the amount, the number of moles. Good. All right. So again, you've got a long section here. You can see you've got 2 marks, but the examiner's given you 1, 2, 3, 6 lines. If we're good with our language, we use the right language, we're going to save ourselves some time from filling in all these lines. And the other thing the examiner said was that students wrote and wrote and wrote and filled up these 6 lines, but why on earth didn't they make it easier for the examiner and put a bulleted list of things that they were going to do? And then it's easier for the examiner to mark, and it's easier for you because you've structured your thoughts. You haven't written down a whole sort of long essay about what you're going to do. You've had a bulleted list, and that's very clear for you. You can correct yourself quite easily, and it's clear for the examiner as well. So it would be, if I was going to do this list, it would be something like, number 1, calculate the amount of the magnesium nitrate. Now, you can see I've used that word amount in there, and that technically means the number of moles. And so I saved myself 3 or 4 words. I'm getting a little bit faster. And I can calculate the amount using N, the amount, is equal to the mass divided by the molar mass. That's the equation that you use when you're calculating the amount. Because if you remember, we were determining that mass, weren't we, by difference. We did a subtraction earlier on to work out the mass of magnesium nitrate. The molar mass, you can use your periodic table to work that out. You've determined the mass by the differences, and you've looked up the molar mass, or you've calculated the molar mass, so you can calculate the amount, the number of moles of magnesium nitrate. Of course, you can do something very similar. You can calculate the amount of magnesium oxide. Remember, you heated the solid to a constant mass. You've got a value for the mass that you calculated by difference for the magnesium oxide. And again, you're calculating the amount, the number of moles, so you're using exactly that same formula. The amount is the mass divided by the molar mass. And then you had another mass measurement as well, because you measured the flask before the nitrogen dioxide bubbled through, and then you measured it afterwards. You measured that by difference as well. So this is getting a little bit boring for me, because calculate the amount of nitrogen dioxide. And again, yeah, we can calculate that amount because we had a mass. We measured that by difference, and we can divide it by the molar mass. All right, so we've got 3 bullet points. They're quite fast to write because they're all the same. We can then calculate, calculate the amount of oxygen. Now that's slightly different because we don't have a mass of oxygen, instead we've got a volume of oxygen. But it's very similar. So the amount of oxygen is the volume of oxygen divided by the molar volume, which was 24.0 decimeters cubed, wasn't it? Okay, so we've got the amount of magnesium nitrate, the amount of magnesium oxide, the amount of nitrogen dioxide, the amount of oxygen. And then you want to work out the ratio of these amounts. So These will all come to numbers to, say, 3 or 4 decimal places. And to work out the ratio, you've got to, ratio of amounts, you've got to divide all the amounts, you've got to divide through by the smallest amount. Yes? And what you should end up with, you'll end up with some values for these amounts here, and then we'll have, once we've divided through, we should have a ratio of 1 oxygen to 4 nitrogen dioxide to 2 magnesium oxide. Oops. There we go. So we'll end up with these ratios. Yeah. Now, probably what will happen, because you're doing an experiment, those won't be exact ratios. You might have 1 there, you might have 4.01 there, you might have 2.10 there, you might have 2.14, something like that. So you're going to divide through, and then because these are amounts, and they're the ratios that you see in the equation, then you're going to have to round, aren't you, to the nearest integer. And that gives, and this is where the language comes in again, when you see an equation with those coefficients in front of the formulae, those are called coefficients of stoichiometry. So those are the stoichiometric coefficients. All right, so what, instead of saying, if you look at this, where was the equation we did here? Okay, that number there is the stoichiometric coefficient. And so this is a stoichiometric ratio. Okay, so if you put that word in, the examiner knows that you're properly talking about this ratio here, the ratio of the amounts, or the ratio of the number of moles. The proper language for that, I'll just write it in, you round to the nearest integer to give the, that's a T, stoichiometric, there's a T there. You've worked out from rounding up this ratio here to the nearest integer, you've worked out the stoichiometric ratio. Okay? So, I think, if you put all that in, the examiner's absolutely happy with all of that, because we haven't written a whole long description, we've just written a bulleted list. It's very easy to mark, it's clear you know what you're doing. You've organized your thoughts, you've shown the examiner exactly what you're doing, you've calculated these amounts, you've used the correct technical language, and then you've divided through, and you know that you've got to get to a whole number later on because you're dealing with stoichiometry, a stoichiometric ratio. All right, and of course, they're going to ask you something about safety as well. Well, they gave you a clue about that earlier on. If you look back in the question right at the start, they put this big box here, haven't they? Like a health warning here. Okay, you've got to be careful about the nitrogen dioxide gas that's being produced. All right, so when we drew the diagram, we made sure that everything was airtight, there weren't any leaks, and that's because we wanted to do good science. We didn't want to lose any gases anywhere, but having airtight connections is also a good safety tip as well, because it means that none of the dangerous nitrogen dioxide gas can get out. And so, not only is it important for good science, but it's important for safety as well. So, I mean, they're only looking for one mark here, aren't they? But they are asking, it's one of these questions where they're asking, so that's plural. What precautions would you take? So I think the examiner is looking for more than one precaution, even there's only one mark. So one precaution, you'd say that the apparatus is checked to make sure that it's airtight. so that no gas can escape. And 2, well, there's always a chance that something goes wrong. You know, you heat up the heating tube, and often when you heat glass, not often when you heat glass, but sometimes when you heat glass, it just cracks. You know, it shouldn't do, but you know, 1 in 100 test tubes cracks, just happens. Or maybe you accidentally use the Bunsen burner on a piece of glass tubing that was weak or something like that. So you should do this inside a fume cupboard, so that if the glass does crack and the nitrogen dioxide gets out, it immediately gets extracted through the fume cupboard. So we're taking these precautions. We're making sure the apparatus is airtight, and we're doing the whole experiment in a fume cupboard to reduce the risk of exposure to the nitrogen dioxide gas. Okay, so that gets us to the end of this first question. And yeah, we've been through the kind of points that the examiner was picking up. All right, so let's move on to the next experiment. And in my experience, these cell experiments or cell diagrams or electrochemistry seems to be one area that students find, I don't know, somehow more difficult than other areas of chemistry. So we'll just do a little bit about this. There is a convention for drawing these cells, and it's correct, it should be, that in the exam paper they've drawn the cell according to the convention. You'd hope so, but anyway, they've done that. And the convention is that on the right-hand side you have the reduction, because if you remember, this is all about a redox reaction. And so you've got a reduction, that's the first part of the redox, and the electrode or the system on the left-hand side is the oxidation. So the convention is when you set up to draw one of these cells, that the oxidation is on the left and the reduction is on the right. And that's called the anode, that's called the cathode, that's negative, that's positive. And if we didn't have a voltmeter there, then the electrons would be moving this way if the voltmeter wasn't there. Okay, I mean, I know the voltmeter's there in this example. So, but what it means is that this electrode has got electrons on it ready to move, and this electrode is positive, ready to attract the electrons. And so that way round of drawing the cell to have the reduction on the right-hand side and the oxidation on the left-hand side is the way that you'd normally draw these cells. And just for me, one way to remember that is reduction starts with the letter R, and that goes on the right-hand side. Yeah, so that's just a kind of way to remember this. The other two things that people use to remember this work is a couple of mnemonics. Oil rig is the one that everyone uses, which is oxidation is loss and reduction is gain. And you can see here that's true because electrons are being lost from this side, which is the oxidation, and they're being gained on this side, which is the reduction. So that's one mnemonic you can use. The other one that sometimes people use is that one, which means the cathode is where the reduction is, and the anode is where the oxidation is. So the cathode and the reduction and the anode and the oxidation go together. So I've got a cathode, haven't I there, and reduction. So those two go together, and I've got oxidation and an anode, those together. So that's another little kind of mnemonic that people use to help them draw these diagrams. That's a little bit of a side chat, but I think you'll see when we come to the end of this question, having some of that knowledge could actually help you a little bit in this experiment. Okay, good. So we're going down here, and you've got to fill in the values over here. That's just plugging numbers into your calculator. The only thing I'm going to say here is that, because it helps us a bit later on, is that mathematically, when you calculate a logarithm, can you see you're calculating a logarithm there? You're just punching the numbers into your calculator, isn't it? The rule in maths is that the number of significant figures that you have in the data, so that we've got how many significant figures there, would you say? Happy? 3 significant figures? The number of significant figures that you have in the data, when you take a logarithm, you should have the same number of decimal places. So we're expecting, under normal conditions, 3 decimal places. And that's the rule for logarithms. Okay? It's not a rule for any other calculation that you do, but when you're using logarithms, the significant figures that you have in the data become the decimal places number in the logarithm data. All right? But up here, the examiner is saying, well, okay, you've got to calculate these logarithms to 2 decimal places. So when you do this on your calculator, you're doing a lot of rounding, aren't you? So, you know, if I was following the mathematical rule, I'd be rounding from 3 decimal places to 2 decimal places. But anyway, the examiner's telling you to do the rounding anyway up here, all right? And you get these kinds of numbers. They're all negative, aren't they? So, you can look these up in the mark scheme, but there's just something I've got to say about some of these numbers. And you keep on going down there, and you get to minus 3.7 at the bottom. And because the examiner is asking for 2 decimal places, the examiner complained that some students, when they got to this point, just wrote the number 1, okay, which is not correct, because you're being, you know, when you write something like that, we don't know whether that's 1.1, 1.2, 1.3. It looks like it's been rounded. So to remove that ambiguity, you should be having the right number of decimal places. So it's 1.00 or 1.40, and don't just do a 2 there, it's 2.00. Okay, so even though you think you're just plugging numbers into a calculator and doing a calculation, the examiner is testing that you know how to properly show 2 decimal places. And then when you came down to this number here and punched in the values into the calculator, the calculator came up with something like 3.66. So 6. I'll scrub that up. The calculator comes up with 3.699. So what should be the value that goes in there? Some students were putting in 3.69. Okay, so the examiner is checking that you're rounding properly, because you've got 3.699, and so that's actually closer when you do the rounding to 3.70 than it is to 3.69. All right, so you would have lost a mark if you put 1 or 2 without the 0, 0, 0, 0 there, and you would have lost a mark if you put 3.69 rather than 3.7. You've got to get your rounding right. And even though you think you're just plugging in numbers from your calculator, the examiner is looking over your shoulder and making sure that you're doing the rounding properly. Okay, good. All right, now this is where you can do a much better job than me, because I've got this really kind of shaky computer pen here. And it's quite difficult for me to see all the graduations on here. So you'll have done a better job than me. And what they've done is, if they've given you the axes all marked up, yes? You've got the labeling done, and you've got the values done. You've got the labeling done at the bottom here, and the values there. So, you know, in other years, they've expected students to label the axes and fill in the graduations as well. it's, for some reason, they're making it easier for you in this particular paper. I don't know whether that'll happen every year. In this year, they gave the students the graduation. So that makes it a lot easier. And you just have to fill in each of the data points. And the convention is you either draw a little cross or you draw a dot and a circle. Now, so if you're plotting a point, it could be a cross or it could be a dot and a circle. Okay, because what happens is the dot is so small, no one can see it, so you draw a circle around it to show that there's a dot in there. And it doesn't matter really which one you use, as long as you don't mix them up. I'm just drawing them there to show you the different styles you could use, but you've got to choose either a cross or a dot and a circle. Personally, I would always use a cross, because later on the examiner asks you, are there any anomalous data points? And you might have to mark them up. You don't have to do it in this exam, but you might have to do it in another exam. And the way to show that you're excluding a data point because it's anomalous is to draw a ring around it and say, I'm not using that, which is fine with the cross, but you've already drawn a ring around the dot anyway. So if a dot was an anomalous data point and you'd already drawn a ring around it, the way to show an anomalous data point that is a dot with a ring is to draw another ring around it. and that's, it just seems that you could get into difficulties with that. So I don't know what style you normally do, but the easiest style seems to be a cross, and then if it's anomalous, you're going to draw a ring around it. So I think using crosses is the easiest. Okay, so don't assume this is drawn to scale or anything like this, but basically, how many data points did you have? 1, 2, 3, 4, 5, 6, 7, 8. I say 8. So that's good. Just so while we're there, in an experiment, having at least 5 data points is good. So they've got 8. So they've easily covered having the right number of data points. So we've got 8 data points, and you will have plotted them, and they will have been, well, you'll have them correct on your graph. There's something like that. Okay, 1, 2, 3, 4, 5, 6, 7, something like this. Anyway, you'll have plotted them, and later on, the question is asking you to draw the line of best fit. So when you do that, you're trying to you need quite a long ruler to do this, but you've got to make sure that when you draw the line of best fit, you have the same number of points above the line of best fit as below the line, which is quite difficult on this because they're so closely on the straight line anyway. That's going to be a straight line. Okay, I don't have a ruler. You guys do. Okay, so that should be a straight line with the same number of data points above and below the line. But in this occasion, you can see actually they're almost all on the line anyway. And so the question is, well, are there any anomalous data points that we want to draw a circle around? And here, the examiner is kind of playing with your head a little bit, because you're expecting, aren't you, from the style of the question, for there to be anomalous data points. And of course, there aren't any. So you've got to say, are there any anomalous data points on the graph? Well, there isn't on this occasion. So you have to say, well, there are no anomalous data points. If so, circle the points. Well, we're not going to circle anything because there's no anomalous data points. And we've got to give a reason for your answer. This is a pretty strange question, actually. So, I mean, the reason there's no anomalous data points is, I can't write here. You would get anomalous data points if there was experimental error. If someone hadn't taken a measurement accurately or hadn't measured a concentration. So there's no anomalous data points because there is very low experimental error. But if you look, there is a small amount of, they're not all exactly on the line, are they? So there's a small amount of scatter. So we're trying to get 2 marks here, aren't we? So we could try and explain why we get this small amount of scatter. Now, one of the reasons for the small amount of scatter is, do you remember that we were rounding up here? And the rule of rounding was that if there's 3 significant figures in the data, there should be 3 decimal places in the logarithm. And so there will be some rounding that means that the numbers aren't quite as accurate as they might have been. So a small amount of scatter due to rounding. Now, the other thing that was missing from the mark scheme, actually, because they identified that one, if you look at the mark scheme. The other thing, if you have experimental error, the way to reduce experimental error is to have replicates. You would normally take a measurement 3 times and get an average. And if you've got a little bit of error, then it all gets averaged out. So you could say, well, that you've got some scatter. Well, that's due to some of the rounding, but the scatter is also due to no replicates or mean value calculation. You didn't calculate an average. You didn't calculate a mean. And so the scientific way to remove experimental error is to take replicates, normally 3, and to get an average. And in this case, they didn't do that, and so they had some scatter in their results. All right. Now, this is called the Nernst equation. And it allows you to calculate the voltage of a cell by looking at the standard cell potential, plus a little bit of a calculation over here. And what the examiner is trying to get you to spot is that even though that doesn't look like it, that is exactly of the form of the equation of a straight line that you know from your earlier maths, y equals mx plus c. So you just have to look at that and think, well, exactly why is that y equals mx plus c? Well, if you write it out more carefully, that's the cell potential. And then you've got that bit there. Can you see? I'll just circle it, which is minus 0.06 over n. All right? So I'll just put some brackets around that. And then that's multiplied by the logarithm of the concentration. Yeah. We don't know how many positive charges it's got. Okay, plus the standard cell potential. Now you see that negative sign is there, isn't it? That's it there. Okay, so when you were doing maths, you'd say something like the equation of a straight line is y equals mx plus c, where m is the gradient and c is the y-intercept. And y is that one there, isn't it? The y-intercept is that one over there. X is actually all of that, isn't it? The logarithm of the concentration. If you look back at your graph, can you see the x-axis is the logarithm of the concentration? And so the gradient, m, is all of that. So the examiner is expecting you to spot that Nernst equation, if you just move things around a bit, exactly fits the equation of a straight line. And you've plotted y against x, you've plotted the cell potential against the logarithm of the concentration. And that means that the gradient of the line is minus 0.06 over n, where n is this number of charges up here. So you've got to use that information to calculate a gradient. And the gradient, you just need to choose, excuse my straight lines, you've got delta y, the change in y, and you've got the change in x, haven't you? Now the change in x is a positive number because you're going that way along the x-axis. But the change in y is a negative number. That's a gradient which is going downhill, because gradients, you normally think of them as going like that, don't you? That's a positive gradient, and that's a negative gradient. And so your change in y, because it's a negative going downhill gradient, the change in y is negative. So if you use your ruler or do your calculations and you work out that value for your change in y and that value for your change in x, then you work out that, what did I get? So for me, I got the gradient was the change in y, which I had as 0.06, and my change in x was 2.05, and that's all negative, isn't it? Because it's a negative gradient. Okay, so that was my gradient, and when I punched that in the calculator, that came to 0.02927. And you can see I'm being good because I'm not rounding up my numbers too early. We can round up at the end. Okay, so we know that that's, you'll have a slightly different number depending on how you calculated the gradient, but it's going to be pretty close. So negative that number is the gradient. And then we know that all of that represents the gradient as well. I'm running out of space here, aren't I? So we know that 0.06 divided by n, which is the expression we had from the Nernst equation, equals our gradient. And we just calculated that from our graph, which is 0.029, excuse me, 27. Okay, negative. And then if you rearrange that to make n the subject of the equation, for me, I ended up with n equal to 2.05. All right. Now, again, because n is an integer, it's either one charge or two charges or three charges, it's not half a charge or anything like that, then one of the things the examiner said is that some students stopped at that point because they'd calculated n. Nothing wrong with that. But n, of course, up here is the number of charges. So the final step on here is to say that you've got to round that to the nearest whole integer. Is it 1, 2, or 3? Because they told us that in the question setup, didn't they? That n is 1, 2, or 3. Well, n, in that case, is closest to 2. So make sure that you're rounding to a whole integer. And the examiner was knocking off marks for students who didn't round to the whole integer. Okay, very good. So that was the gradient, the y equals mx plus c, the m part. But we've got to calculate, haven't we, the standard cell potential. And that's the c part. That's the y-intercept. And this is just sort of playing with your minds a little bit, because when you think of your y-intercept, you're normally thinking of an intercept over there, aren't you? That's your y-intercept. But remember, the y-intercept is at x equals 0. That's where your y-intercept is. All right? So you've got to do your y-intercept where y equals 0. Now, y equals 0 is not there, but y equals 0 is there. So on this occasion, can you see how they're playing with you? You're sort of thinking a bit. The y-intercept, you extrapolate. I'm losing my pen there. Extrapolate. And the y-intercept is where y equals 0, which is there. What am I saying? I'm saying x equals 0. That's where the y-intercept is, isn't it? Sorry. Did you understand what my mistake there? I mean, the y-intercept is where x equals 0. Happy with that? Okay. Because the y-intercept can't be 0, otherwise the y-intercept would be the same every time. Okay, so my mistake. So the y-intercept is where x equals 0, and x is 0, not here. X is minus 4.5 there. X is 0 over here. So that is the y-intercept. And actually, because I've kind of sketched this graph, the y-intercept, when I measured it, was 0.9, what did I get? I got 933 volts, okay? Or because you're working to 2 decimal places, you've got 0.93 volts. Losing my pen again. Okay, there we go. Now, in all this electrochemistry, even though the positive sign is implicit, it's always good to have positive or negative. Well, you should always put a negative sign, but even though we normally have an implicit positive sign, we should actually specifically say that the standard electrode potential is positive 0.93 volts. Okay, so use your graph to determine the standard electrode potential of the cell, where we drew the y-intercept where x equals 0, and so the standard electrode potential of the cell is equal to positive 0.93 volts. And then you've got to do this calculation down here to work out the standard electrode potential for M. We don't know what that is. Now this is a bit tricky because you know that the standard electrode potential for silver is 0.8, and you know that the cell is 0.93. So you've got a couple of options, haven't you? You could have that the cell potential, the standard cell potential, is 0.8 for the silver minus 0.13, because that equals the plus 0.93 that we calculated up there. Yes? So that's one way of looking at it. Or the other calculation you might be doing is saying that the standard electrode potential of the cell is 1.73 minus 0.8. And that also gives you 0.93. So we don't know, do we? I mean, it's one of those, but which one is it? Yeah. And there's a couple of things here. You could just look at the data that they give you, because at the end of the paper, they give you a kind of data sheet. And so is this other potential? We know it's a metal, don't we? They told us that it's a metal. So we're looking for a standard electrode potential for a metal that is either negative 0.13 or positive 1.73. Now, if you look, there's no metal, is there, that's anywhere near positive 1.73. So that immediately excludes that. But if you look down, there's a couple of metals that are close to negative 0.13. So, well, the standard electrode potential for the lead reduction, these are always written as reductions, aren't they? These equilibria, is negative 0.13 volts. So that fits. Yes? Okay. All right. So that's the way you can work that out. But later on, we'll go right back to our cell diagram and see if that all makes sense a bit later on. Right? That's why we did that bit about the anodes and the cathodes and the right-hand side and the left-hand side a bit later on. Okay, so that's the way you work that out. You've got 0.13 volts, and that matches up against a metal because they gave you that in the question. It's a metal. Yeah, and all the things that have all the redox systems, all the reductions that have these positive standard electrode potentials aren't metals. They're non-metals, actually. So we're pretty sure, we're very sure that we've got the identity of M correctly because we're trying to find a metal. And then we've got to write the overall reaction. And the overall equation is one of these redox reactions, isn't it? So there's going to be a reduction and an oxidation. And the normal way that you make a redox equation is from two half equations, one that is a reduction and one that is an oxidation. And so that's a little bit tricky because in the table here, they've given you, as you always do for these electrochemical series, you've got a list of standard electrode potentials all written as reductions. Now, one of them will be a reduction, but the other one can't be. You've got a redox, you've got a reduction and an oxidation. So one of them has got to be reversed because it's an oxidation. We've got to work out which one. So this is the one that we just identified. You've got iron 2 plus 2 electrons, its equilibrium, its reduction to lead. And then you've got your silver. It's only got a 1 charge there, hasn't it? So it only has 1 electron and its reduction to silver. And we just calculated that that's 0.13 volts. And we were told earlier on that that is plus 0.8 volts. And so your trick for doing this is to say, well, the electrons leave the negative electrode and go to the positive electrode. If you think about electrodes, that makes sense. Electrons would go to the positive electrode. The electrons are negative. So that means, in terms of electrons, the positive electrode would gain electrons, wouldn't it? The electrons are going there. And the negative electrode would lose electrons. The electrons are leaving there. Yeah? And so once you've worked out which is the positive and the negative electrode, or the more positive electrode, then you can work out where the electrons are being gained and where they're being lost. And once you know where they're being gained and lost, you've got your mnemonic of oil rig. And so if they're being gained, that must be reduction. And if they're being lost, that must be oxidation, using our little mnemonic there. Now, if they're being lost, then this equation here is correct, isn't it? Because the lead is losing its electrons. No, I've got that wrong. Let's start with the gain, that's easier. Okay, which of these is, this is the gain, isn't it? So the silver ion is gaining an electron, that's easy. So that must be the reduction, yes? And if that's the reduction, the silver ion is gaining an electron, this must be an oxidation, yes? So that means that we're going to have to reverse this equation to show that electrons are being lost. So if we reverse that round, we have that. Okay, so, and you can see because we've got electrons on this side, electrons are being lost. And because we've got electrons on this side, for silver, they're being gained. So we've got things the right way around. And that means that we've got to combine equation 1 up there with equation 2 down there, because we reverse this equation here. And to combine them, we have to have the same number of electrons in each equation. And one of the things the examiner picked out was that students somehow kept putting a 2+ for silver. We had that actually in the mark scheme earlier this week. So why students do that, I don't know, but they do. Well, I don't think we're doing it in the room, but silver is 1+. And so we're going to have to multiply that equation by 2 so that both equations have the same number of electrons. So multiply that up by 2, 2 silver ions, 2 electrons gives us 2 silver metal. And once we've got the same number of electrons in each equation, we can add them together. We add the reduction and the oxidation. We add the red with the ox, a reduction and oxidation. We've got a redox equation from 2 half equations, and you get the lead plus 2 lots of the silver ion is going to the lead and 2 lots of the silver metal. And you should also just make sure you've done a good job there by including state symbols. So the lead is a solid electrode, and the silver ions are in solution, they're aqueous. And you end up with lead ions in solution, so they're aqueous, and the silver is deposited on its electrode, so the silver is solid silver metal. So we've written the overall equation for the reaction that's taking place. That's a redox equation, isn't it? And we've just got to answer here for the salt bridge. Okay, so this sometimes catches students out because the salt bridge goes in, doesn't it? Just when you're drawing, and you might not think about it even more. But if you come over here and try and understand what's going in the salt bridge, we've got the silver ion with its 1+ going to silver metal, haven't we? All right, and that solution will be silver nitrate. All right, so the other ion that's there, although we don't see it, is the nitrate ion. Yes. Now, what's going to happen is that initially all the nitrate ions are balanced by all the silver ions. That's fine. We've got 1 nitrate ion for every silver ion. But what's happening during the use of the cell is the silver ions are getting used up, aren't they? Because they're becoming silver metal. And so these silver ions are being used up, which is leaving the poor old nitrate ion without a balancing positive ion. All right? So where can the silver ion get its balancing positive ion from? Well, it can get it from the salt bridge, because the salt bridge, you'll see later on, we could put in the salt bridge a salt potassium nitrate. And so when the silver ion gets used up, we just replace it with a potassium ion, because we've got potassium nitrate in the salt bridge. And every time a silver ion is used up, we can pop out of the salt bridge a potassium ion. And so the nitrate ion here is always balanced by a positive ion initially, by the silver plus ion, but during the experiment, increasingly by potassium plus ions, because we've got to replace the silver ion that was used up with some other ion, and that other ion can be an ion from the salt bridge. In this case, we can use potassium. It's a good replacement for the silver ion that was used up. So that was a bit of a long answer, but why is the salt bridge necessary? Well, good language there to maintain balance of charges. I think that's the language they used in the mark scheme. And what you mean by that is the silver ion is being replaced by a potassium ion. Yep. Now, last bit then, they haven't told us, have they, what salt goes in the salt bridge? Yeah? I don't know. I mean, I've told you, haven't I already, that it's potassium nitrate, but it could be potassium chloride, or you could choose some other salt to go in the salt bridge, because the ions that are in there, their only job is to replace the ion that got used up in the cell. So, well, why not use potassium chloride or something else? Why do you use potassium nitrate? So that's where they're driving at in this last question here. Are you going to put into the salt bridge potassium chloride? Are you going to put in there potassium nitrate? Are you going to put in there potassium sulfate? You're trying to design an experiment here. Which one are you going to use? And the reason you're going to use that is because that you know that if you think about a table of solubilities and insolubilities, then for nitrates, all nitrates are soluble, so they're really great for the salt bridge. But for chlorides, like sodium chloride, potassium chloride, that they had potassium chloride up here, then lead and silver chloride form insoluble precipitates. And that's no good, because if you had some chloride ions around, suddenly you'd end up with precipitates inside your cell, which you don't want. You don't want that. So you can't use potassium chloride, because you get a precipitate of silver chloride and a precipitate of lead chloride, because we discovered that lead was the other ion earlier on, didn't we? And you also need to know that when you come to sulfates, that lead, if I could get my pen to write, come on, pen, just trying to draw a B here, there we go. Can you see that's a B? That's a lead there, PB, yeah. And barium sulfate as well. These two, lead sulfate and barium sulfate, are also insoluble, and they form precipitate. Now, you might have come across that insolubility rule in tests before. So a test for silver is to add chloride, and you get a precipitate of silver chloride. Or a test for sulfate is to add barium, and you get a precipitate of barium sulfate. So you have to know a little bit about these solubilities and insolubilities, but you can't use potassium chloride, because we'd get precipitates of lead chloride and silver chloride. And we can't use potassium sulfate, because we'd get precipitate of lead sulfate. But we can use potassium nitrate, because all nitrates are soluble. So you've got to get 2 marks here. If you consider it to be any unsuitable, explain why. You're going to say that KCl and potassium sulfate are not suitable because PbCl2, AgCl, and PbSO4 would all form and are insoluble, in brackets, form precipitates. Okay, and I think that was it. We got in there all the comments that the examiner made, plus we were very careful, I think, during this session to focus on vocabulary, things like knowing amount for the number of moles, and the stoichiometric ratio, or the stoichiometry, is the integer numbers that you see when you balance a chemical equation. So that was good. And I think we got through that, didn't we, in less than an hour. It was only an 1.5-hour paper, so that was good. We got all the examiner comments in. We went through the whole mark scheme. And if there's any more comments that you'd like to make, then, of course, all the Z coaches are on the Slack channel. Very, very interested to hear from you and your comments. And as always, I wish you every success with your chemistry studies in A2 for Cambridge International Exams. Okay, that's it. Okay, good. So I just have to do that end bit at the end to kind of wrap up, because a lot of students might be listening on YouTube or elsewhere. So we'll do that little bit at the end just to wrap up. Good. All right. Okay. Yep. So is that your data book there? Yeah. Okay.
I got some questions.
Yes.
So on this diagram,
yes,
I got like I didn't wrote these things. If I just put
Yes.
water bars,
Yes.
is it okay?
Yeah, that is. Yeah, that's the kind of apparatus you might have used in chemistry already.
Yeah.
That's absolutely fine.
Okay.
The gas syringe is something that you might use at A level because a lot of students break them when they're younger and they're very expensive. So you have to wait till the students are older.
Okay.
But that's absolutely fine.
Okay.
I guess, apart from the fact you're using more expensive equipment, that's why you use them when you're older.
Okay.
Here, I suppose, there's always a danger, isn't there? That some of the gas, the oxygen gas, might dissolve in the water. So, for that reason, a gas syringe is a bit more safe than rubbing something through water.
Okay.
And I think the mark scheme said that was okay as well, didn't it? What you did was fine.
I mean, there's like no diagrams.
Yeah.
Like examples.
Yeah.
Diagrams, but I didn't.
So there's no diagram.
Yeah.
So, but the mark that's being awarded is the student collects the gas in a syringe or over a liquid.
That water. I'll get it.
Yes. So this was fine. So you wouldn't have lost a mark there at all.
Okay. Yeah.
Okay. And the reason the gas syringe is mentioned is just because you don't lose any through gas dissolving, and you're unlikely to break expensive equipment. Good. All right. Well done. Yeah, I don't know how to turn this off. It's the problem. So I'm still going live. Okay. So I've just got to stop the Google Hangout somehow, haven't I? Okay, so if I go to the browser.
Stop broadcast.
Yeah, that's it.